Welcome to the Explainer. Today, we're going to tackle a huge concept in algebra, the composition of functions. Now, I know that sounds a bit intimidating, right? But trust me, by the end of this, you'll see it's really just like building an assembly line, but for math. So, to get our heads around this, let's start with a simple question. How does the day of the year actually determine your heating cost? Well, think about it. Your heating bill depends on the temperature outside, right? And the temperature outside, that depends on what day of the year it is. You see that chain reaction, that dependency? That is exactly what function composition is all about. Okay, so here's our game plan. We're going to start with the building blocks themselves. Then we'll dive into how to hook them together to make our assembly line. We'll even run a few examples through the system to see it in action. And to wrap it all up, we'll look at where these things pop up in the real world. Sound good? Let's go. All right, first things first, let's start with the absolute basics of our assembly line, the individual machines themselves. So, what is a function really? Just think of it like a super simple, super reliable machine. You put one thing in, that's your input, and it spits out exactly one thing, that's your output. Every single time. No guesswork, no surprises. One in, one out. Okay, so we've got our individual machines, but here's where it gets really interesting. What happens if we link them up? You know, when the thing that comes out of the first machine immediately becomes the thing that goes into the second machine. Well, that's when we've built ourselves a process, an assembly line. And in the world of math, we call this a composite function. Now, that notation might look a little weird at first, right? That little open circle. But all it really means is f of g of x. And that just tells you the order of operations. You do the g function first, take that answer, and then you do the f function to that answer. This picture really says it all, doesn't it? It shows the flow perfectly. Our starting material, x, goes into the first machine, machine G. What pops out? Well, G of x does. And that piece doesn't even hit the floor. It goes straight into the next machine, machine F. And the final finished product that comes off the line, that's our f of g of x. Okay, if there's one thing you need to burn into your brain, it's this. This is the golden rule right here. You always evaluate the inner function first. You have to work from the inside out. It's just like an assembly line. You can't do the second step until you've finished the first one. It's as simple as that. All right, theory time is over. Let's actually put this into practice and see how it works. We're going to build out your how-to toolkit and look at the three main ways you'll see these problems, with tables, with graphs, and with formulas. Okay, first up, a table. Let's say we need to find f of g of 3. Where do we start? Inside. So we look at our table and find g of 3. See it? The table says it's 2. Perfect. Now, that answer, 2, becomes the brand new input for our outer function, f. So we go back to the table and look for f of 2. And boom, the answer is 8. See? Inside, then out. Believe it or not, it's the exact same idea with graphs. Let's find g of f of 2. We start with the inside function, which is f. So on the f graph, we find 2 on the x-axis, go up to the line, and see what the y value is. Got it? Now you take that y value, and that becomes your new x value over on the g graph. Find it on the x-axis, go up to the line, and read the final y value. It's just tracing a path. And last but not least, we've got formulas. And guess what? It's the exact same inside-out process. To figure out f of h of 1, we handle the inside first. We calculate h of 1 by plugging 1 into its formula. That gives us 5. Now we take that result, 5, and we plug it into the outer function, f. And f of 5 gives us our final answer, 20. Same logic every time. Okay, so this whole inside-out thing brings up a really, really important question. With our assembly line, does the order of the machines actually matter? Like, could we just swap machine F and machine G and still get the same thing at the end? What do you think? Let's take a look. Here we've got two functions, f of x is x squared and g of x is x plus 2. On the left, we're doing f of g of x. So first, x goes through the g function becoming x plus 2. Then that whole thing goes through the f function getting squared. The result, x squared plus 4x plus 4. Now look at the right. We swapped the order. We're doing g of f of x. So first, x gets squared. Then we add 2. The result is just x squared plus 2. Totally different, right? And the results speak for themselves. X squared plus 4x plus 4 is definitely not the same thing as x squared plus 2. This proves a super important point. In regular multiplication, order doesn't matter, right? 2 times 3 is the same as 3 times 2. But with function composition, order is everything. It completely changes the outcome. So we've spent all this time building these assembly lines, right? Chaining simple functions together to make something more complex. Well, it makes sense that we should be able to go backwards too. We should be able to look at a complicated function and take it apart, reverse engineer it to find the simpler machines it's made of. And this process has a name. It's called decomposition. It's literally like being a detective. You're looking at the final product that rolled off the assembly line and trying to figure out what the individual steps, the individual machines were that created it. And let me tell you, this is a super useful skill to have, especially when you get to stuff like calculus. And the good news is, it's a pretty simple two-step process. First, you just look at the function and try to identify an inner piece. You're looking for some simple operation that's kind of tucked inside a bigger one. Once you've got that, you just have to define the outer function. In other words, what's happening to that inner piece you just found? Okay, we've gone through the how. Now let's talk about the why. Why does any of this matter outside of a math classroom? Let's bring it all home and see how this seemingly abstract idea is actually super powerful for describing the real world. The truth is, once you know what to look for, you'll see function composition is everywhere. Seriously, think about a retail sale. First, there's a function for the 30% discount. Then, there's another function for the extra 15% off that new lower price. That's a composite function. Or how about a ripple from a raindrop in the pond? The area of that circle is a function of its radius, but the radius itself is a function of time. It's a chain reaction. What do all these things have in common? Function composition. It's kind of like the secret blueprint, the underlying mathematical language for how one event causes another, which causes another. It describes any chain reaction or sequence of events. Once you see it, you can't unsee it. So here's the big takeaway. The thing I really want you to remember. Function composition is way more than just a textbook exercise. It's a powerful way of thinking, a lens that helps you see how interconnected everything is. It's the language of how one event triggers the next, creating the complex systems we see all around us. So, I'll leave you with this question. Think about your own day. What's an assembly line process that you're a part of? Maybe it's cooking a meal or a workflow at your job. Can you break it down? What's the inner function? What's the outer one? It's a fun way to think about it. Thanks for joining this explainer.